So, any questions about last time? So we're still trying to figure out how to deal with sets at the same time, looking back and to logic, and so see if we can get anything useful here. So, and we will. Okay. So the definitions of intersection and union are here. So they're very useful as they are on the just for sets. So whatever mathematical objects you're dealing with, whatever this number theory or calculus, it doesn't matter. But also we remember it is in fact corresponds to logic, right? So in fact, if I take these two definitions, I could write them slightly differently. So just remember, so x belongs to A and B if x belongs to A and belongs to B. So how would I then? I could just write it out is equal to x belong those x's that x belongs to A. Well, to make that point, let me make this circular like this, and here I will put this symbol. Remember, which simply stands for and. So x belongs to B. Okay, so the match then makes a lot of sense. Then the hat is either a hat, a rectangle, or it is a rectangle or circular, but it's kind of a similar shape. And then you do the same with the union, except I'm going to use this, right? So and the rest is the same, as a matter of fact. So A union B is those x's that x belongs to A, x belongs to B, except now it's either one or the other. Okay. So once again, intersection, same sets possibly, or it belongs to one or the other, and so all of them are included. Okay. So well, there remains the third operation. Remember, so these are the three operations. The third operation is the complement. Okay. So the complement. So intersection, union. Complement is slightly different. It is like a subtraction, or very much like subtraction, except if you want to speak of the complement, it is like there is a bigger set that includes everybody else, and that's the one we are dealing with. So we assume that given X that contains all sets that we care about for now. Okay, so this is how I draw it, like this. So this is my A, and this is my X. Okay, so and then we're talking about the complement. The X is the universe, A of all possible statements that it can make within some reasonable limitations for us, and then we would pick a set in there. So so the complement is well, let me just illustrate it. This is the complement, right? So the notation is x minus A. Okay, so the minus is turned into slash, backslash, even though sometimes you see actual minus. I don't know. I prefer this for the time being. So in other words, it's all x's and y's. How do we write it? How do we write it in the set notation? X does not belong to A. That's right. So you don't even have to mention X capital. That is because it is assumed to be there, and everything you talk about is here. So, for example, if you talk about real numbers, you don't have to mention that's a real number, or just say it's a number. Or if you talk about integers, you might limit yourself to those exclusively. So from the context, usually X is clear, or if it's not clear, then you have to ask. Okay, so okay, does not belong, right? Okay, so what about as you can see, this statement, however, does not the right out here does not match the what I have here in the first two lines. So in the first two lines, I match the set operation on the left with a logical operation on the right. What is the logical operation on the right for the complement?
What did that slash mean again?
Well, that's what is written. What is that? What it means? This is the definition.
Oh, okay.
There is no trick here. We are saying what it is. So certainly the illustration is good, but really ultimately it is what's written is as the definition. So by definition, it's all of those x's that do not belong to A. That's all there is. Okay. So for example, if A is even, then x minus A is all even. That is all odd. Okay, so once again, dead alive, odd even, divisible by 3, not divisible by 3, all of those examples you can think of are there. So you take the complement of one, you get the other, and vice versa, right? So the complement of the complement, what is it?
All even?
What?
All even?
No, I mean I meant in general.
That would be the null set, right?
It will be what?
The null set?
No.
No.
The complement of the complement. Think a picture. What? What?
It's like the original set.
The original set, right. So the complement of odd is even and the complement of even is odd. So complement of odd is even, complement of even is odd, so you come back. So it's not like subtraction. It's more like reciprocal maybe, right? So reciprocal, the reciprocal is the reciprocal, okay? So 1 over x, 1 over 1 over x is x, like that, okay? Okay, so that's one example. That pretty much what happens is we split then our set x and A into two sets that do not intersect, right? So A intersection with the complement is empty. On the other hand, the union with the complement is the whole x. Okay, so that's what I describe as split. Another word for it is a partition. This one has two elements, two sets. Sometimes you can certainly split sets into more than more than two, but the main properties are the same. They cover the whole thing, and they do not intersect with each other pairwise. Okay, so we'll see more of those. But what remains here is I still want to go all the way back to logic and describe the complement in terms of logic. As you can see, the definition right there. So can you make it slightly different? X does not belong to A. What is the logical way to put it?
X belongs to the complement of it?
No, that would be, yeah, you could, but that way we're going to go all the way back to then you ask what the complement is, and you explain complement in terms of the complement. No, that's still sets. I'm talking about logic. So the well, what's missing? Yeah?
Implication of that?
No.
Implication?
What? No.
Negation?
Negation. This is a statement. X belongs to A. Negate it. Okay? So that's what I was talking about. So if you want to really to match set operation on the left and logic operation on the right, that's how you do it. You negate that statement. X belongs to A. What's the negative? X does not belong to A. Okay? So it's a nice match, and so that way we can go always back and forth, whichever you find easier. I think sets are easier to understand because all of those illustrations are very straightforward. You can think of real numbers to illustrate any kind of logical, set operations or properties of set operations or algebra of set operations. They're very descriptive, very easy to illustrate with those little diagrams. Not so much with logical statements. You may have noticed that in the last homework. So I want to circle back to that and talk about that's the match, right? One of the challenges was to negate statements in the homework, and then this is how you can work your way back and understand the negation in terms of the complement. Okay, so then some of the now the question becomes how do you how do these three operations interact with each other, and primarily what happens to the complements of, let's start with the intersection. What is the complement of the intersection? That's the first question I would like to ask. What is the complement of the intersection? And you realize that the question corresponds in logic to what is the negation of and, right? So what, if you remember what it is, or if you don't remember, then with sets it's very easy to illustrate, even just with pictures. So I have A here, I have B there, right? This is A and B. This is once again X that contains everything, X. Okay, and then we're talking about the intersection. So that's my intersection. A intersection B is right here. And now let's draw the complement. So it's everything outside. Let me do it in a gradual way. So suppose, in case it's not quite yet clear what I'm talking about. Oops, not quite right. Less so. Okay, so let me just remove things that are not relevant, or at least we would like to ignore them for the time being. So let me mark the complement. So I mark this is the union intersection, right? And now we're talking about its complement, right? So I just take that purple one and color everything that's not purple. Okay, so this is it. Correct? Right, so it includes some of A, some of B possibly. The picture on the left is generic, right? So there are two sets that we know nothing about them, so we can assume that there might be some intersection between them. So that's the way it should be understood. Okay, so carefully. Okay. So all good. It might help you if you're talking about some sets, and you can actually mark the meaning of the whatever entities, mathematical things you were dealing with. You might mark them here on the picture. It might help you to understand things. But what we're trying to do is be above all the specifics of the problem, or specifics of whatever you're dealing with, but rather do it purely in set theoretic sense. So we want to express somehow this new complement. So what I'm talking about is what here in blue here is X complement and intersection B. We want to work our way in such a way that, like over here, see, it was on the left was something complicated. We carried out some algebraic computation. We realized that it is the same A. Okay, it is really algebra. Okay, so that's what I want to do again. So, do you see it? The answer? How do I express this purple in terms of the original sets A and B? Any thoughts at all?
Change the and to an or.
I could. So, well, yes. What do you mean? You're saying that let's change the intersection to union, right? So, okay, union of what then?
Not A and not B.
Not A, complement A, complement B. So let's do that. So I will, well, actually, and one more. Let's take, we are doing negation, and we know that we're gonna if we did negation, we want to do complement, which is negation, which means there will be negation of A and B, and then we just have to combine them somehow. And that's the idea that was suggested, is to take the union of the two negations, or the union of two of the complements, or the or of the two negations. So this is what I do. I'm gonna on the left, I'm gonna do complement of A. This is the complement of A. Right? And here I will do the complement of B. Okay, do you see it? So these two combined together through the union give me the whole thing over there on the right. Okay, so once again, what am I looking at here? So on left I have the complement of A and the complement of B here. Okay? And then well, there you go. So then what we're claiming to have here is X minus A union B. A intersection B is X minus A union X minus B. So, okay, so we have seen something like that, right? I don't remember what the example was, but so once again, two conditions are, if you look at the original statement, logically you have two restrictions, and they have to be satisfied. Think about two equations, right? Two equations, and you're solving a system of equations. And what does it mean? It means, say, I don't know, X plus 1, we'll do that one again, like that. So you have two restrictions on x, y's, okay, and then they have to be satisfied simultaneously, okay, and now what is the complement of the solution set? It is those x and y's that what? That don't satisfy the system. What does it mean, not satisfy the system? It means that you don't satisfy both of the equations, but rather you might satisfy one. If you satisfy one but not the other, you still fail. Okay, so that's where the union comes from. So it suffices to violate one of the equations, one of the conditions, in order to get failure, get into the complement. Okay, so that is a simple explanation of either logically you can think about it set-wise. So let me actually take that equation over here and use it once again as an illustration of what we're doing here. So we have two lines. This one is x plus 1 is equal to 1, and this one is, if I'm not mistaken, x minus y is equal to 1. Okay, so then where we started with the intersection. So this is set A, this is set B, right? So with the intersection, this is the intersection, right? So A intersection B. And then what do we do? Now, what is the complement? It's of that point. It is everything else. Everything else but this point, the complement of this. And so what is it? You just take the if it is feasible to draw it, but I could try again. So I take the complement of 1. It's a bit hard to try to draw the complements. So that's the complement of the first line. So it's a cut, right? And then you take the complement of the other. Like this. Complement of the other. Oops. So in other words, so it's a piece of paper with one cut and the other cut, but then you take one piece of paper with a cut in it and the other piece of paper with a cut in it, and then you put them together. So then the only piece is missing is the point, that point over here. So the only thing remaining will be here. That will be still missing. The rest is not missing anymore. Okay, so as you can see, logic and sets are just you go back and forth entirely. So I mean, a solution set to an equation is a set on the xy plane on one hand. On the other hand, what is it? It is a statement. It is a statement. Xy satisfies the equation, right? And then the complement exactly corresponds to the failure of the equation to be satisfied. Okay, so feel free to use it. Well, let me write it out as a logical statement. It will be what is it? A and B negation is A negation or B negation, right? So the lesson that we saw when you negate, you kind of tend to flip things. So and is flipped. You flip the statement themselves. No, you negate the statement themselves, and then you flip the and into or. Okay. Well, then you guess we already have noticed that several times that the and turns into or, but or turns into and. So. And same thing happens with the union and complement. So let's examine that. So let's start with sets once again because it's so easy to illustrate. So I will be doing the same thing, except I'm going to be starting with the union. And then the question is, what is the complement of the union? We already know the answer, but let's do it anyway. So what is what? What is the complement of the union? So once again, we have A, we have B, X here, A union B. What does it look like? This looks like this. Okay, and we'll have it. Okay, so it's the same thing pretty much. Okay, I just need to erase this. Okay, so and then I complement it, right? So what I'm left with is this. Complement whatever is not purple is now marked with green. Okay, so this is indeed as claimed complement of A union B. Okay, and once again we're trying to figure out how to express it in terms of the original sets, right? So remember how? Well, we can already certainly guess how. It should be in terms of on one hand, we know that when we do a negation, the negations or the complements of those sets will appear. So the complement of A and complement of B will appear. And how are they combined? How? What? And. No, not and. Well, that's the confusing part. And is union sounds like and, but it's actually or. Okay, so it will be the intersection. So and, but intersection. Okay, so if you think about it, we're looking at what's on the right. In green is all points that lie outside of A and B simultaneously, not either one or the other. Okay, so. For a point to be outside of this, it would have to lie simultaneously outside of A and simultaneously outside of B. So let me mark here A on left. I'll put A union complement of A again. I guess I could have just used it. Right? That's complement of A. and this is complement of B. But both of them are kind of too large, right? So I'm going to get the what I'm after, the green one top right, if I go with the intersection. Okay, so once again, this is x minus a, x minus b. Okay, and then they give me the intersection, so whatever lies simultaneously outside of a on the left and outside of b on the right, and that gives me this one. Okay, so let me write it out. I write it out then. X minus a union b is x complement a intersection x complement b. So once again, you notice how the union turns intersection. When you negate, union turns. We flip this one, and in the previous case we flip the other one. So they flip into each other. Okay. So whenever you do the complement, underneath I'm writing the logical statement, which is A or B. Complement is complement A and complement B. Okay. So this is the algebra that we can use if we so inclined. Certainly, it's a pure common sense. Sometimes it gives you a shortcut, especially the actual mathematics is complicated. Then whatever you can do in a mechanical way, you probably should, because that saves you hard thinking and also possibilities of mistakes. So we'll do that. All of these will reappear whenever we face something more complicated. Okay, so sets will appear whenever necessary, as well as the logic will try to negate things. We're going to negate them using these properties. So they, as you can see, they come in pairs, and they're flipped into each other when you negate. So flip when negate, when you do complement, or when you do the negative. Okay, so that's the idea. So once again, the flip and the negative are the same thing. And then, well, we had another pair. We treated simply. By the way, these are called conjunctions. Conjunctions and or. And then in logic, we also had the other two symbols, not operations, but symbols, and those are for any and there is. And they're also flipped into each other when you do negation. Okay, remember that? So, so a little bit back. For any, say, x, ax, if I negate this, it will be, there is an x, which is a complement of ax. Okay? And then vice versa. There is so if I negate there is an x such that ax is true, then the complement is for any x, ax is not true. Okay, so that's what we did. So once again, flip the quantifiers. So there are two then categories. These operations are the conjunctions, and then there are quantifiers there in the preamble. And then now the third, there is the yet one more, which is has proven itself more challenging, and that's the implication. And how do you negate the implication? And it is tempting also to try to flip it in the opposite direction, so just don't do it. Well, let me illustrate it. Why we don't do this in logic? We don't do it because we don't do it in sets. So if A implies B and I try to negate, this is not equal to A. Okay. what in fact, what's the meaning of the second statement?
If not B, then not A.
Right, so but what is it? Relative to the original statement, this one. What? It's a contrapositive, which means that they are equivalent. So you're trying to negate it, and then if you do this, you end up with a contrapositive, which is the equivalent to the original, so you certainly don't want that. That just simply does not work. They're reversing the arrows, negating the two statements and flipping the arrow in the opposite gives you the contrapositive. It does not give you the negative. Okay. Why? Well, if it doesn't seem logical, it certainly takes some time to get used to, but it's easy to see if you go with sets. So remember how A implies B means that A is a subset of B, right? And then, okay, so A is a subset of B. So this is, say, B, and this is A. Well, maybe, let me start over. Maybe a better picture. A and B. Okay, so that's what we have. That's what the correspondence between sets and logic and logical statements is right here. So saying that A implies B is like A is a subset of B. Right, so where is it? There is. It is, you can go backwards if you want to. So I made this step, but I could go backwards if I just how do I describe what I have on the right? I say X belongs to A, then X belongs to B. Okay, so back and forth, logic sets, same thing. Okay, so and now if we try to negate it, so we try to negate the situation, either described algebraically like this, or diagrammatically described by this picture. So let's say A remains the same. So I'm trying to negate. Well, if I try to negate, what is it? A is a subset of B. Well, let me keep B. That's a pretty big one. So suppose this is still my B. What are possible positions of A relative to B? So this was my A. But I want to now consider the universe of possibilities when A does not satisfy this property. So what does it mean? Can you imagine? What should be the diagram? Where should I place A?
On the outside of B?
Can you be more specific?
Um,
If you say no, it's the correct answer. No, you cannot. So it should be on the outside somehow. So this is okay,
okay,
but this one too.
okay.
Okay, so that's the problem with negating the statement, is that you cannot really say where exactly A is located. Does not have to entirely lie outside of B, because as you can see, that second A is not inside of B, so it's a possibility. Okay, so this is that picture that I'm looking at right now is in fact the negation of the statement on the right. So let's try to express it. A is a subset of B. Let's try to express it. Can you express it its negation? A subset of B negation based on this picture. Now maybe let me help you out. What if we also have X for our convenience? Does it help? What's so special about A?
We're using both of the red A's? Or just...
Well, kind of. One would be sufficient, but just the second one is more important, I suppose, because it's more generic. But the second one, just keep in mind that it could be entirely outside of B, but might be only in partial. So how would we state it? So I want to So what's so special about that A? It sticks out of B. That's the thing. So right, that one. This is the what makes a difference is this part, right? So that on the original statement over there, A was entirely inside of B, so there was no part like this. So this one is also good, but it's just not generic because the whole A is outside of B. So the second one is more important. This one, okay. So how would you describe this? That picture that you have, yeah.
It'd be A and not B, or A.
And not B what?
The negation would be complement B. So it'd be
So A, well, let me write A and not B, okay. X minus B. So what is the relation between them? Look,
Or,
no.
or,
Let's see, I think sets.
intersection.
Intersection is
And, right?
is non-empty. Okay? So that part that sticks out has got to stick out for us to, the condition on the right to fail. So not the whole thing of A lies inside of B. So there's a piece of A that is outside, which means that there is that piece of A that lies entirely within the complement. And so, in other words, A intersects the complement of B. So as you can see, with sets, so this is what I'm saying. The negation of A subset of B is A intersects the complement of B. Okay. Now try to go back. Let's go back to logic. Let's go back to logic and try to understand this. So once again, we are trying to negate the implication. And as you can see, it might look kind of awkward. Okay, so if you remember, especially some of the examples from the homework. So well, let me try. Let me do it with the parameters. So A now is statement. So suppose there's an x there. So maybe we're talking about equation or something like that. So x is a parameter. So this is how I would write it. For any x, ax implies bx. Okay? This is what we want to negate. Yeah. So we just taking one step away from sets. So this will be negate. So we already know what to do with for any. There is an x, okay? But then we also know, so where is that there is x? There is an x. Here it is. This is the x. There is an x outside of B, which is also inside of A. So, well, there you go. There is an x which is simultaneously makes A correct and makes B incorrect. Okay? That's the logic that will work out. So I don't remember if there was something like that in the yeah, there was in the last homework. So it came up last time. So here it is. When the prime and odd, there's only two here, but let's say let's throw out two, so it would be standing in the way. So suppose prime and odd is our statement. So number is x is prime and odd. So just to illustrate the last discovery, so x is prime. No, I'm sorry, that's not the right one. I need the one that has an implication here somewhere.
245-degree angle.
Okay, yeah, let's do that. That one has two properties. That's why it's problematic. Now let's make it up. So x is prime well, how about this? X is odd, then X is prime. Okay, it's wrong, but who cares? Okay, X is odd and, no, that's it. So X is odd, X is prime, and we're trying to figure out its negation, right? So you can very easily translate that back into sets, and you'll see the answer. But or you can use what we just discovered here, and write out the answer. So first of all, and that's always a good idea to start with when you see a statement like that, and you're talking about some number x, which comes suddenly from nowhere. Make sure that it comes from somewhere. Okay, so what should precede the statement? If I want to make this, well, let's say if x is odd, then suppose it's written entirely in plain English. Okay, so if x is odd, then x is prime. How would we, just before we do any kind of sets or algebra or anything like that, let's just write it out in the proper way. Remember, so what do I start with? It is a statement about all x's. So for every x, that's right. It starts with for every x. Okay, so that 90% of theorems in mathematics start with for every of something. In this particular case is a number. Okay, and then if I want to do it in implication, what do I do? The first statement is x is odd, and then the second one, x is prime. Okay, so that contains everything, and it puts in the familiar form of inclusion. Okay, so I'm sorry, of implication. Okay, so now we have a formula on right. This is how we negate it, right? So negate. What's the negative of the statement now? There exists an x such that what? And not prime, that's right. X is odd, and x is not prime, or it is composite. Okay, so that's the whole thing. So it makes sense, right? So
Would it be or instead of and, since you said you had to flip?
no, it has to be simultaneously odd and not prime. So even though, think about this, even though the condition is satisfied, the conclusion fails. That's what we're talking about. For some x, at least there is an x for which that implication that we claim in the first statement fails. How? Even though the condition is satisfied, the conclusion does not. Okay? There is another trick for dealing with this if you were, well, that's a little bit of a formula to remember, even though if you do it a few times, it will become automatic. Another way is to avoid implications altogether. So that's another possibility of how to negate complex statements, which, especially if-then statements. Here's another one. The trick is, so that's one method, the same statement, but this is the first statement. What I'm going to do is I'm going to use expanded quantifiers. So in other words, I will throw out implication altogether. So how can I restate this without an implication? So there is, in other words, there is no if and then. Well, I still have to start with for any x, but how about this way? X, for any odd x, comma, x is prime. It's the same statement, but there is no if-then. And for any odd x, x is prime, so that's the statement. And then think about it, we know how to negate those. Those are easy to negate, right? Because for any, and then followed by the statement. So how do I negate this? That's right, there is an odd x. X is not prime. Okay, so just another possibility. And it is that what I called an odd. There's an odd x, X is not prime, what I called it the expanded or extended quantifiers. So you can sneak in some extra information with the quantifiers, and together they will form what? The condition of your implication. And if you did that with the whole condition, then condition disappears, and you're left with what's left, with a conclusion, without implication necessary at all. Okay? So that's just a fancy way to say what I just illustrated here. Okay, so what else do we... Complements and how they interact with each other, negatives, complements, unions, and intersections correspond to the conjunctions, and the set algebra of sets, it is in fact behind it always there are quantifiers. So the quantifiers is either for any. So for example, if you say that A is a subset of B, it means that every element of X is, well, let me write it nonetheless. So A involves of B. Okay, so we can go back to quantifiers for any X in A, X in B. Okay, and then what is the corresponding value for corresponding statement for if it is there is an X in A, X in B? What am I talking about here? Just read it. If X, there is such an X that is in A and in B, what is it? What am I saying? So
Is that a negation of?
intersection? No, it's not a negation. Intersection, and what about it? What about the intersection? Non-empty. So that's non-empty means that there is an element there, and that's the X. Okay, so if it is for any, it is usually about inclusions. So logical, if you see a statement that is for any, then it will there's an inclusion somewhere. If you're talking about there is, it is about non-empty intersection. Okay. Okay, thank you.